So guys, in the previous class, we have seen some of the multi-level indexes, right? So if you look into the multi-level indexes, basically one kind of tree is ISAM tree, indexed sequential access method tree, and another kind of tree is b-tree. These two kind of trees we have seen in the previous class, right? So what will be the time complexity of a b-tree? Big O of log n. If order of the tree node is going to be m, then it is going to be big O of log n to the base m, right? So coming to the differences between ISAM tree and the B tree, what might be the major difference? One is in static in nature, means once the memory is created, you cannot able to deallocate until the entire data is going to be deleted, right? Whereas coming to B tree, it is going to be in dynamic in nature. Based upon the way that you are trying to insert, the tree is going to be synced from bottom to top. If you are going to delete it, you are going to, it is going to be grow when you are going to insert some data. It is going to be shrink when you are going to delete the data. So based upon the data, it is going to be responded. We call it as dynamic in nature. Whereas coming to ISAM, it is going to be in static in nature. Right? This is what we have seen in the previous class. Now in today's class, we'll see further extension of B tree. We can call it as b+tree. B+tree, right? So the reason why we are moving for b+tree is we have some of the drawbacks that we observed in B trees. So those to overcome those drawbacks, we are moving for b+trees, right? So the time complexity of B tree is big O of log n to the base m. If here m value is going to be 2, then it will be act as a what? Binary search tree, right? Means based upon this m value, your tree height is going to be depends, right? If m value is very less, tree height is going to be more. If m value is large, tree height is going to be decreased, right? Suppose for example, we are going to have huge data. For example, if I say some 10,000 records are there, something like that, right? So for example, if I try to say this is a kind of trees, right? Now my data is distributed over all the levels. Right? Something like 4. Here it might be 3, 1, 2, 6, 5, and 7. Right? So now, what is the meaning of this one? It is a kind of a B tree of order 2. Meaning that maximum number of children are 2. Right? Now, how your data is distributed? Your data is distributed over all the levels or not? Yes. Data is distributed over all the levels. That's the reason when you have seen the structure of the B tree node, what we are trying to say, n number of block pointers are going to be there, and you are going to have search key, and for each and every search key there will be a data pointer. Or we can say it as record pointer. Then how many will be there like that? n-1, which should be less than or equal to size of the node. Right? Now here the question is, as your data is going to be saved in the internal nodes also, number of children are going to be decreased. Right? Now you may have a question, if I am not going to store the data, then can I increase the number of children? If I am not going to store the data, can I increase the number of children? Yes, because see, I have given mention already, right? So for example, block size is 512 bytes, right? Then number of block pointers are 10, and number of keys are something like 9, and number of record pointers is something like how many record pointers are there? If number of keys are 9, that means number of record pointers are there 9, and this will be also 9, and if it is 9, this will be 10, something like this. I mean, what I am trying to convey to here now, if there is no record pointer, there is no record pointer, definitely there might be some space or not. There might be some space. How much space it is going to be left? N minus 1 into record pointer size is going to be free. If n minus 1 into record pointer size is going to be free, in this particular place, can I place more number of block pointers? If I place more number of block pointers, what does it mean? I can be able to increase the number of children. If I am going to increase the number of children, the height of the tree is going to be decreased, right? So as number of children are going to be increased, height of the tree is going to be decreased. And what about width of the tree? Increases, right? If width of the tree is going to be increased, height of the tree is going to be decreased, then what about the time complexity? Decreases. Time complexity is going to be decreased, right? For example, if I say that log n to the base j is the time complexity for b+tree. Time complexity for the b+tree, and log n to the base m is the time complexity for b-tree. Then what might be the relation between m and j? J greater than m. Very good. Why you are saying that it is j greater than m? J means what? Order of the node, right? As order of the node is increasing, its height is going to be decreased, right? Height means what? The time taken to search for a particular value, right? So that is the advantage of b+trees. Means in b+trees, we are going to have n block pointers, and n minus 1 keys are there at non-leaf nodes. What might be the leaf nodes data? So here there is no data. When you think that there is no data, the data should be exist somewhere, right? The data is going to be exist at the leaf level, right? So how it will look like now? 4, 3, 1. I think this structure is wrong, right? So here it will be something like 2 and it will be 3. We can make it modify. If I say it is 2, it is going to be 2 and 3 and 4 and 5, 6 and 7. Now this particular example will be the example for b+tree. Why means I already mentioned, if you look into the non-leaf nodes, in non-leaf nodes, is there any data pointers? No, there are no record pointers, or we can say there are no data pointers, right? If there are no data pointers, there should be certain location where it has to be maintained. That maintenance is going to be done at the leaf nodes, right? That is the reason you got duplicates. Here you got 4, here also you got 4, here you got 2, here you got 2. What is the meaning of these 4, 2 and 6? Those are search key values. Meaning that if you look into the structure of non-leaf nodes in b+trees, you are going to have simply the value which you want to search key along with block pointers. Whereas coming to leaf nodes, you are going to have what kind of search key you are going to search. For each and every search key, you are going to have number of record pointers, meaning that it is going to point it to actual data. And also there is simple modification is there. There will be connection between one leaf node to another leaf node. Connection between one leaf node to another leaf node. That's why we can say that how many block pointers are required now to connect one leaf node to another leaf node? One block pointer is enough, right? So this size should be less than or equal to total block size of the leaf node. Right? If I say n, this one, n into search key into block pointer plus block pointer is less than or equal to size of the block. Is it okay, everyone? Right? So the reason why I am trying to say here now, so the one more advantage of b+tree is, which is meant for the purpose of to perform range queries. To perform the range queries, we are going to use b+trees. Whereas coming to b-trees, if you would like to search some data between 3 and 7, right? How many times you are going to search? First I will try to take the value 3. I will try to start searching from the root node. 4 less than 3 less than 4, then 3 is greater than 2, then I will come here. Yes, 3 is available. Then I will go for 4. Again I need to start searching from the root node. For 5 root node, for 6 root node, for 7 root node. Meaning that for each and every search operation of the range queries, I need to start from the root node. That is the problem what we are going to face in the B tree. Coming to B+tree, once you start searching from the root node, first I will start searching from the any one of the set like 3. Is 3 less than 4? Yes, I will go to the left side. And is 3 greater than 2? Yes, I will go to the right side. Then I will go for the exact record. From here onwards, I won't go back. I will try to start searching towards until I require data. Because here you are going to have pointers. You are going to have pointers. This is where the B+trees are going to be helpful, right? Meaning that in leaf nodes you are going to have data pointers. This is the difference between B trees as well as B+trees. So that is the reason its advantage is going to perform range queries, right? And also as the tree height is going to be reduced, the time complex is also going to be reduced. Okay, fine. So this is the main concept behind B+trees. Then can you answer what about the order of non-leaf and what about the order of leaf nodes? Is it going to be vary or is it going to be same? So the order of non-leaf nodes as well as order of leaf nodes are going to be different or going to be same? Definitely different. Why definitely different? Because in non-leaf nodes we don't have the concept of record pointers. So that space can be utilized for some other purpose, right? Okay, fine. So try to solve this question. For example, there are some records are there: 5, 10, 12, 13, 14, 1, 2, 3 and 4, right? I am asking you to construct a B tree of order 3. Then what will happen? Check here, right? This we are going to have 5, right? We are going to have 2 children, there is no problem. If I insert 10, there are 3 children, there is no problem. If I insert 12, then definitely there is going to be a problem. For that, what you are going to do? I will simply take out the middle one. I will make it extracted towards higher side. So you are going to get here 10. Next I am going to get the data 13. There is no problem. If I got the data 14, there might be the violation of the B tree rules. Now what will happen? Again you are going to select the middle one and you will try to split into multiple nodes. If I am going to split it, you are going to get 13 and here you are going to get 14. Now next thing is I am going to get the value 1. Yes, there is no problem. Next I got the value 2. If I got the value 2, it is going to be violated at this particular node, right? Because of to make like non-violation, I am going to move this towards the top side. But when you move towards the top side also, here also it is going to be violated, right? At that situation, here 2 will become and 10 will becomes to the top side, right? So if I try to redraw it, 10 will be the root node and 2 will be the left side, 13, 1, 5, 12 and 14. Now if I am going to add 3, there is no problem. If I am going to add 4, again we need to restructure it, right? If I am going to restructure it, what might be the answer? I will try to directly write. Here we are going to get 4. And this will be the middle one. And here you are going to get 4 and 5. Hope you have this idea, right? How to construct this B tree of order 3, right? Is there any problem? B tree of order 3, right? Is there any problem? 4 is duplicate. Okay, right, now it is okay. So this is b-tree of order 3, right? If you are able to observe, my entire data is going to be distributed in all the locations, right? So that is the reason I am saying that every search key contains one record pointer also. And you know, on the left side as well as the right side, meaning that for n keys you are going to have n plus 1 block pointers, right? According to terminology you have to understand, right? Fine. If you try to construct for the same data, we will try to construct b+tree, right? So you can check, it is somewhat different. b+tree of order again 3. Order again 3. If b+tree of order again 3, it is going to be having how many keys? How many keys it is going to be? 2. How many keys it is going to be? It is going to have 2 keys, right? So first I will try to take the first node 5. Is there any problem? No. Then I have taken the 10. If I took the 10, there is no problem. Then I will consider the 12. If I consider the 12, definitely there is going to be a problem. If there is going to be a problem, what you are going to do? You are going to take out the middle one and you are going to make it move towards the, growing towards the upside, right? 5, 10 and 12. 10 and 12. This is what actually in b-tree is going to be happen. Okay, fine. But the thing is here, if I am going to write simply like 5, 10 and 12, right? What is the concept of b+tree? In the leaf level, we should have the data. We should have the data, right? So means somewhere you have to maintain the record 10. You have to maintain the record, right? So what are the possibilities? I can place the record 10. I can place at the left side or I can place at the right side, depending upon the logic what you are going to do. For example, I am trying to write at the right side. So here we are going to get 10. Here we are going to get, right? So you may write the same thing in different way also. 10, you are going to get 5, 10 and 12. So this is all according to your requirement. There is no problem. Okay, fine. Now try to insert the value 13. When you are going to insert the value 13, is there any problem? Again, it is going to be a violation. If it is going to be a violation, again you need to make it split here. If you are going to split, you are going to get 10, 12. Here you are going to get the value 5. Here what might be the value? 10 you are going to get. And here 13 anyway, you know, we have to add 12. Why we need to add here? Because in the leaf level you have to maintain the data pointers. So you are going to get the 12. Now try to insert the value 14. If I am going to insert the value 14, again it is going to be violated. If it is going to be violated, again I need to move towards upside. Here you are going to get 14, 10, 12, 14, again it is going to be violated. So you are going to get again upside. So if I try to restructure it, I am trying to write directly. So what is the root level? 12, good. And left side you are going to get 10. Here you are going to get 5. It will be 10. There is no change in the left side. Right? What about the right side? It is 14 or 13? 14. 13. So middle node you need to change, right? 13 it should be. And what about its right side? Only 14 or 13, 14? 13, 14. What about the left side? Right? If you are able to observe, so far what are things that we did? All are going to maintain at the leaf level. Right? So actually, when you are trying to draw, it should be connected like this. It should be connected like this, right? So now, try to insert the next value. Next value is going to be 1. 1, there is no violation. If you are going to insert the value 2, again there is going to be violation, right? If you are going to insert the value 2, your tree might be 12. 2 will be coming here, right? And 10. Here you are going to get 1. Here what might be the values? 2 and 5. 2 we need to maintain. And here 10. Good. Next, I think right side there is no change. 13, 12, 13 and 14. All are going to be connected like this. Next, I am trying to insert the value 3. If I am going to insert the value 3, again it is going to be violated. If it is going to be inserted value 3, it will becomes here, it is going to violate it, again it will move towards right side. Right? So what might be the root value? 3 and 12. Left side is going to be 2, middle it is going to be 10, right side is going to be 13, and here it will be 13, 14, it will be 12 only. What about the left side? It should be 1, right side of 2, 2, only 2. What about here? It has to be 3, 5. Why it has to be 3? I am going to maintain the internal load structure of the value always in the leaf level. 3 and 5. Anything's missed? 10 should be here. Right? Next, try to insert the value 4. Try to insert the value 4. When you are going to insert the value 4, I think again it is going to be violated. It is going to violate, right? So the final tree will look like this. 3, 12, 2. Here it will be 4 and 10. 4 and 10. It should be 13. Here it will be 13 and 14. 13 and 14. And here it will be 12. And on the left side, you are going to have 3. Here, is it 5 or 4, 5? 4, 5. Good. It should be 4, 5. And here it should be 10. And on the right side, you are going to have 2. Here it will be 1. Right? So I think all are done. So if you are able to observe clearly, all the values are going to be placed at the leaf level. Meaning that my entire data is going to be placed at the leaf level. And what about all these? These are going to be simply search keys. Simply search keys, right? These are just going to be meant for the purpose of searching, right? So when you are trying to increase the performance of searching, especially for range queries, when somebody asking for to find out so and so something between two values, then you are going to use the b+trees. b+tree, that's it, right? So if you are able to observe, the height of the B tree and height of the b+tree are going to be same in this aspect. But with respect to searching, definitely b+tree is going to be best one, right? When you are going to have large set of values, definitely there is going to be height also differences between B tree and b+trees. Okay, now. Right. So based on this, can you able to define the formula again? If I am going to have a non-leaf node in b+trees, what is the formula? I may have n block pointers plus n-1 keys, search keys, which are going to be less than or equal to size of the block, right? Whereas coming to leaf nodes, you are going to have what? Is there any block pointers here? Yes, there will be one block pointer, but not n, right? So how many keys are there? N keys are there. And each key is supposed to have one record pointer. Along with that, there is a block pointer. This size should be less than or equal to n. Okay. Can you able to construct the tree for the given values? 1, 4, 7, 10, 17, 21, 31, 25, 19, 20, 28 and 32. Try to construct the tree for this one. b+tree. b+tree of order 4. You may take anything, but better to take order 4. What might be the answer? So your answer will look like, it will be root node is 17, left side is 7, 20, 25, 31. This will be 31, 32. 25, 28, 20, 21, 17 and 19, 7 and 10, they are going to be 1, 4. This is the final tree after construction of b+tree for the given data. Right? You can just cross check. Right? Right? So you can observe here the question. This is the given gate question. What they are asking is, it is a b tree of order 3, b+tree of order 3. Get all the records with a search key greater than or equal to 7 and less than 15. Right? So finally they are asking for how many nodes you are searching. How many nodes you are going to fetch when you would like to solve this particular query. Right? For that, what you can do, select the number 7. 7 is less than 9. One node you selected, and 7 is greater than 5. Another node you have selected, and you are going to start searching here. 7, 9, 11, 13, and 15. Right? So total how many fields, how many nodes you have searched here? Completely 5. That's it. Right? So it's a kind of 1 mark question. Okay, so we have created so far the b+tree, right? So let us try to do the b+tree deletion. So which is same as like the b tree only, right? When you are going to get certain value, like v, what you are going to do, ma? You are trying to start searching from the root node, and wherever you observed the respective value, you are going to simply delete it. But before going to delete the respective value, what you have to do, you have to check the conditions, right? Minimum condition is, if I say m is the order of the tree, then there should be m by 2 minus 1 keys. Minimum m by 2 minus 1 key should be there, right? If it is going to be satisfied after deleting, then we can go for simply delete that. After deleting it, you have to check once again one more thing. What you have to check? There may be the data present in the internal nodes. So at that time you have to start deleting from the internal nodes also, right? Similarly, if your records might be less than minimum of m by 2 minus 1, then what you have to do? You have to completely rebalance the tree. Right? Complete rebalance the tree. How we are going to rebalance the tree? You can just take it from the left subtree, or you can take it from the right subtree. Right? If both the conditions are not satisfied, right? Both the conditions are already in minimum nodes, then what you have to do? You have to simply merge them. Right? This is a simple algorithm what you can follow, right? Which is same as like b tree only. Right? Suppose for example, if I try to take the nodes, something like 17, 5, 13, 24, 30, 2, 3, 5, 7, 8, 13, 14, 16, 17, 19, 22, 24, 27 and 29, and finally it will be something like 30, 34, and any other value 38, right? For example, now I want to delete the value 19, right? The value 19. Is there any necessary to check here the value 19? Like here, order of the tree might be 5 only. Order of the tree might be 5, right? So can I say that it is a b plus tree? B plus tree or not? Because it contains duplicates, right? Internal nodes contain duplicates, so I can call it as b plus tree, right? If order of the tree is going to be 5, what might be the number of keys? Number of keys are 2. Number of children's? Okay, in order to avoid confusion, just go with the keys only, right? So keys means what? 5 by 2 minus 1, which will be 3 minus 1, 2. So minimum keys should be there for each and every node should be 2. Okay now, maximum how many are there maximum? Maximum m minus 1, right? So if I delete the 19, is there any problem? No. Okay, fine. For example, I am trying to delete 22 once again. If I am going to delete 22, what will happen? It is going to violate the property like minimum number of keys are going to be failed, right? When the minimum number of keys are going to be failed, what you can do? You can simply rebalance the tree. How we are going to rebalance the tree? By taking the data from the left side or by taking the data from the right side, right? So can I take it from the right side? Yes. If I try to take it borrow from the right side, what might be the value I can take here? 24. But can I take it directly? No. You have to take it through root node, respect to root node, right? So 24 will comes here, then I will get the 24 here. If 24 will come, what might be the here? You have to change the internal nodes also. 24 is going to replace with what value? 27. 24 going to replace with 27. Okay, fine. Because we have taken it borrow, right? So the values which are present here should be less than the value. 27 here, it is the perfect one. Okay now, fine. For example, if we take, try to delete 29. Try to delete the 29. If I am going to delete the 29, is it going to be violated? Yes. To avoid this situation, you can take borrow from the right side one. Can I take it borrow from the left side? No, because it is already having minimum nodes like 17, 24, minimum 2 nodes are there, 2 values. So I take it borrow from the right side. If I take the borrow from the right side, I am going to get 30 here, and this 34 will be the root node. So the values are here 27 and 30. 30, right? For example, if I take one more case, 45, 20, 49, 50, 49, 10 and 20. This should be 45, not 49. So now, if I would like to delete the value 45, delete the value 45, what will happen? Can I delete the value 45? 45 is not less than, so it is greater than or equal to, so I will go for right side and so on. I have my 45 is available here, right? Now if I am going to delete it, you may get question here, what might be the order? Order will be 3. If order might be 3, it's going to have minimum of 1 key, right? If I am going to delete the 45, there will be 0 keys, right? If there is 0 keys, what you can do? You can take it from borrow from the right side or left side. Is there any chance to get from the right or left? No, there is no chance to get it from the right or left. Suppose for example, first, is it going to be b plus tree? Is it going to be b plus tree? No, right? It should be here. 49 should be there. 49 there, right? Now, if I am going to delete the 45, what will happen? Can I take the borrow from the right side? Right? If I take the borrow from the right side, I will get here 49, and here what will be the value? 50. What will be the value? 50, and this there will not be 49 here. So now is it going to be b plus tree now? Yes or no? 40. But what about the root node? We have to rebalance once again. What value you have to place here? Right side smallest value, like, or we can say that unordered predecessor value. in order successor value you have to place, right? So here if I place 49, is it going to be correct tree? I am going to place this one. See, if I am going to redraw 49, 20, 50, 10, 20, 49 and 50, right? So I think it is correct, right? Now for example, I am trying to delete 49 once again. I am trying to delete 49. Now what will happen? If I delete 49, I cannot able to take borrow from the right side, right? If borrowing is not possible, what you have to do? You have to merge them. You have to merge them. Then how can we merge? You have to merge towards the upside, right? So wherever possibility, right? If I am going to merge it, I will get, see, if I delete the 49, this 49 also going to be deleted, right? If I am going to merge it, you are going to get 20 as a root node, along with 20, 50 will be there. 50 will be there, and that 50 will be coming to the right side also. Here it will be 20. This is the final b+tree after deleting the value 40. Okay, now, right? So if you want to have more clarity, try to solve this. If I am going to have the structure like this, 20, 7 and 17, 25, 31, 1, 4, 7 and 10, 17, 19, 20, 21, 25, 28, 31 and 42, right? So it is of b+tree of order 4, right? I want to delete the nodes values in such a way that 21 should be deleted, then 31, 20, 10, 7, 25 and 42. Now tell me how we are going to delete it. So I think this example will clear all our doubts. Right? All cases are going to be satisfied. Right? Now first I am trying to delete 21. If I am going to delete 21, what will happen? Right? How many number of minimum keys are there? One minimum key, right? If I am going to delete the 21, is there any problem? No problem, right? Yes, good. Right? Before going to delete, you have to check in the like internal nodes also, right? You have to make sure 21 deleted, there is no problem. Try to delete the 31. Delete 31. 31 is available here. I can able to delete as it is going to have minimum of 1 key. There is no problem. But the same 31 is going to be available at internal. So what you have to place here? 40. Good. Right? Meaning that you have to place in order successor. Meaning that the smallest element on the right subtree. Right? For this, the smallest element is what? Only one element, that is 42. I am going to place 42. Next, I am trying to delete the 20. I am trying to delete the value 20. If I am going to delete the value 20, there is a problem. Meaning that number of values are going to be 0. Right? At the situation, you can able to take the borrow from the right side. If it is possible. Yes, sir. Right side is going to be having more than minimum number of keys. Right? Minimum number of keys are going to be 1, right? 2 keys are there. So then there is no problem. So I can able to get one value from the right side. Which one you are going to take? You can take the value 25. If I take the value 25, I am going to delete from here. And I need to make this also deletion. This should be what value? 28. This should be 28. Now, deleting this 20, there exists other 20. This 20 also should be deleted. What value now we need to place here? In order successor. What is in order successor here? 25. So, your final tree will look like this. 25, 7, 17, 28 and 42, 1 4 7 10 17 19 25. I think only one value, 25 28 and 42. Now try to delete the next value. What is the next value? 10, right? If we are trying to delete the value 10, is there any problem? No problem, it is directly deleted. Okay, good. Next, try to delete the value 7. Yes, there will be the problem. If I delete the 7, I can able to get the bar from the right side, I think. If I get the bar from the right side, here we are going to get 17, here we are going to get 19. I think it is also very easy one, right? So 1 4 17 19 19, everything is right. And you know the basic rule, right? If I try to perform any kind of operations for the b tree or b+tree, the height of the all nodes should be same, height of the tree, right? In all levels should be completely filled. Right? Now try to delete the value 25. 7. I haven't deleted the 7. It should be here. What value? It should be 17. It should be 17. Okay now. So you may get confused now. Right? So try to observe. I am trying to delete the value 7. If I am trying to delete the value 7, first you have to search in the data location like leaf node, right? As it is available in the leaf node, you are trying to simply replace it with the respective value, right? So what value you have got? Here you got the value 17. You got a 17, right? Now if I make the 17, this also should be deleted. This also should be deleted, right? What value you are going to place here? You should be in order successor. That's it. You should not get confused. It should be in order successor. And here what might be the value you have to place? You have to place the 19. Otherwise, it is not going to have 3 children. This should be the correct order. Okay now. Fine. So next, let me take the value 25. If I take the value 25, what might be happen? Delete the 25 will lead to deleting the index also, like root node also, right? So you have to make sure. If I delete the 25, I cannot able to take the bar from the right side. Taking bar from the right side, then what you can do? You will try to merge up to here. Merge up to here, right? If you try to merge up to here, what might be the location? So this entire thing is going to be 42, and here it will be 28. It will be 42. What might be the root node? Root node will be the in order successor, 28. Okay now. Fine. So try to do the next one. What about the 42 deletion? 42 is going to be here. If I delete this one, here also it will be there, right? If I try to combine with the root node, there is no chance, right? You have to merge it with the left subtree again. So your possibilities are now, what will be happen? If you want, I will try to write the entire thing. First 28, 17, 19, 42, 28, here it will be 42, it will be 1 4, here it will be 17, here it will be 19. Now tell me, if I delete the 42, what can I do? If can I able to merge like this? Can I able to merge like this? If I am going to merge, what will happen? Tell me. Right? Deleting this 42 is also going to delete this one also, right? Now, if I am going to merge like this, how many levels we are going to get? 2 or 1? 1 level, right? See, 28 will comes here, that's it. So, this side if you check, there will be one level is minus compared to the left side. So, meaning that you have to combine the entire tree. If you are going to combine the entire tree, how it is going to be done? You have to make sure like 17, it will be 28. It will be 28, and On the left side, you are going to get 1, 4, 1, 4. In the middle, you are going to get 17, and here you are going to get 19, and it will be 27, 28. Right? Based on the scenario, you have to combine. Right? So always you have to take care of that. All the levels should be same. This point you have to take care, right? So based on that scenario, you have to go with the merging. Right? Guys, you may get question, right? If I take this 19, what will happen again? That will be the again different scenario. It may change. Right? So you have to go with this one. So this will be the correct one. Any doubt? Right? So what might be the differences what you observed between the B tree and b+trees? What might be the differences? One is definitely height is going to be vary. Inner things are there. Right? So definitely B tree is going to have more height compared to b+tree. Right? We can say in terms of time complexity, big O of log n to the base m, big O of log n to the base q, where q is going to be greater than m. This is one difference. What would other differences? Very good. Right? Here data is going to be distributed in all levels. Am I right? That's why record point is going to be calculated for all levels. Whereas coming to here, data is going to be stored in which level? Data is going to be stored only in leaf levels. Here, order of leaf and non-leaf is going to be same or different? Same. Here, order of leaf and non-leaf is going to be vary according to the inputs. Inner things are there. What about the searching? Searching is going to be difficult or is going to be easy? Searching is difficult in B trees, whereas coming to B+trees, searching is going to be easy, right? So especially with respect to range queries, right? When you are going to ask for only one record, then definitely both are going to have the same performance. But when we are asking for some kind of range queries type, definitely B+tree is going to be more advantages. Right? Inner things are there. What might be the duplication? Duplication is going to be allowed or not allowed? Duplication is not going to be allowed. Whereas coming to here, duplication is going to be allowed. Any other observations? What about the leaf nodes? Everywhere they are going to be sorted order. Right? There is no link between one leaf node to another leaf node. Right? Whereas coming to here, there is going to be link between all kind of leaf nodes. This is where your search time going to be decreased. Okay. Now? Right? Suppose for example, if I try to say the search key size, right? So if you take anything, the search key field size is going to be 9 bytes. The search key size is going to be 9 bytes, and block size is going to be 512 bytes. Record pointer, what might be the required parameters? Can you tell? Record pointer is going to be 7 bytes. Block pointer is going to be 6 bytes. Right? Then can you tell what might be the order of leaf nodes and non-leaf nodes? right? So especially if I say it is with respect to b plus trees, if it is going to be b tree, definitely the order is going to be same. Order is going to be same, right? If you are going to calculate it for non-leaf nodes, what might be the answer, right? So if I say, if I am assuming that there will be n block pointers, meaning that n children's, where each children's size is n block pointers plus n minus 1 into key size, that should be less than or equal to 512 bytes. This is for to find the order for non-leaf node, right? What is the value of n? We don't know. What is the size of block pointer? 6. N minus 1 into key size. Search key size is going to be 9 bytes. So if you are going to solve it, you are going to get the answer, right? 6n plus 9n, which is going to be 15n minus 9. If you go towards right side, it will be 521. N value is going to be less than or equal to 521 by 15, which value is how much? Which is going to be 34 point some value. 34 point some value, right? Then what might be value you have taken? Are you going to take floor or seal? You have to take floor or seal. You have to take the floor, right? If it is going to be 34 point, okay, 34 point something, okay, there is no problem. It is going to be fitted. But if you take 35, what will happen? It is going to be beyond 512 bytes, right? I think this explanation is given in the last class itself, right? So it will be definitely less than or equal to 34. Less than or equal to 34, right? So meaning that the order of non-leaf nodes is going to be 34. What might be the leaf node? Leaf node. So in leaf node, how many block pointers are there? Only one block pointer. How many search keys are there? If I am saying that n is the order of the node, n search keys are there. So key size plus each key size can have record pointer, not block pointer. It's a record pointer plus block pointer, which should be less than or equal to 512 bytes. N value we don't know. N into key size is what? 9 plus record pointer is right? 7 plus block pointer size is 6, less than or equal to 512. 16n less than or equal to 506. N is going to be less than or equal to what value? 31 point something. Good, right? So the value of n is going to be less than or equal to 31. Right? If you are able to observe the clear difference here, non-leaf nodes are going to have more number of children. That's the reason height of the tree is going to be decreased. Okay, now why the value is more here? Because we have eliminated the concept of storing record pointers data.